So here, we're going to describe the operations of the proteins involved in the release of transmitter from vesicles and those involved in vesicle recycling. After releasing their transmitter, vesicles have to be recycled, or else the synapse would run out of vesicles and the synapse would become non-functional. The importance of vesicle recycling is illustrated by a normal synapse and one from a mutant animal in which recycling is stopped at higher temperatures. The normal synapse is shown in the left panel labeled A. The two arrows indicate the synaptic region, but the important feature is that there are lots of vesicles in the axon terminal. Next, look at the right panel labeled B. There are no vesicles in the terminal. It is virtually empty. The reason is that the vesicles that have released their transmitter, shown by the arrows, are stuck and cannot be recycled. In other words, the synapse has used all of the available vesicles and the vesicular supply has been exhausted. This synapse is non-functional. Next, let's follow the events that vesicles undergo at a normal synapse. There are two phases. Both are shown here. The first phase is the release of transmitter from the vesicle when the vesicle membrane fuses with the membrane of the axon terminal. After the transmitter is released, the vesicle membrane melds completely into and becomes part of the membrane of the axon terminal. There are several important proteins involved in these steps, and we will explore them in just a few moments. The second phase is the recycling and reconstitution of vesicles from the axon membrane. This starts at number 3 in the figure with the protein clathrin. Clathrin forms a sphere around the membrane, and when the sphere is fully formed, it is pinched off by the protein dynamin. We will discuss both of these proteins later in the movie. After the vesicle is free, it sheds the clathrin coat and forms the reserve pool of vesicles labeled as tethered vesicles in this figure. Those vesicles are actually not freely floating. As we shall see, they are actually tethered to the actin cytoskeleton of the axon terminal. Before turning to the proteins involved in vesicle fusion and recycling, I would just point out that there are an enormously large number of molecules and proteins involved in these processes. Their names are absolutely mind-numbing, but mercifully we are only going to consider 7 of them. So let's first turn to vesicle fusion and transmitter release, and after that take up how vesicles are recycled. Okay, there are 3 proteins critical for fusion and the release of transmitter. The first one I'm going to show you are the voltage-gated calcium channels, but that's not one of the 3, but of course it's very important. The first one is the snares in the axon terminal, shown as little red lines here. These are actually a complex complement of proteins, but we're just going to bundle them together and refer to them as snares. Complementing those snares are snares in the vesicle membrane, as shown as little blue lines emanating from the vesicle. And the third one is, and this one's very important, is synaptotagmin, because synaptotagmin is the calcium binding protein. And I promise you, synaptotagmin will be one of the questions on your exam. The first step in this process is that the vesicle has to dock at the active zone. And what I mean by dock is that the snares on the vesicle bind to the snares on the axon terminal and literally hold it in place. The next event occurs when the action potential sweeps through the axon into the axon terminal and depolarizes the axon terminal. That in turn opens the voltage-sensitive calcium channels, which allows for the influx of calcium. Calcium then binds the synaptotagmin, And the binding of the calcium to synaptotagmin in turn triggers the fusion of the vesicle and axon membranes, resulting in transmitter release, like that. Following the transmitter release, there is a complete fusion of the vesicle and the axonal terminal membranes, like that. So the first phase is complete, and now we have to turn to the second phase, the phase of vesicular recycling, which begins by the actions of two proteins. One of those proteins is adaptins, and the other are clathrins. The clathrins are really cool, and I'm going to tell you a lot more about them in just a moment. But the first point to be made is that the adaptins bind to the synaptotagmin, to the snares, and the other proteins that are still in the axon membrane. Remember, the axon membrane and the vesicular membrane had fused. After the adaptins bind, the clathrins bind. The clathrins bind to the adaptins, and that really begins the whole sequence of vesicular recycling. As adaptins and clathrins accrete onto the membrane actually buckles to form a hemisphere. It actually doesn't look like that. It looks more like this. Right? You can see the clathrin cage in purple. Below that are the adaptins, and below that is the cell membrane. As the clathrins continue to accrete onto the membrane, the complete vesicle begins to emerge. And what I'd like to show you next is exactly how clathrin forms this geodistic cage around the vesicle. I gotta tell you something, because clathrin is really seriously cool. So now we saw how cool clathrin is and how it forms that cage around the membrane. And with continued growth, the vesicle then attaches to the axon only by a neck formed by the axon membrane. Then what happens is dynamine wraps around the neck and pinches the vesicle off of the axon membrane. There's dynamine. Watch. It pinches the membrane off and frees the vesicle from the axonal membrane. Now the vesicle can diffuse into the interior of the axon terminal. The next step is that the free vesicle now sheds its clathrin coat as well as the adaptins. It becomes a naked free vesicle. And once it becomes a free vesicle, what it does is it refills itself with transmitter. The transmitter is actually transported into the vesicle by a special protein in the vesicle membrane called a transporter, but that need not concern us. The important point is the vesicle is now filled and ready to go. And the vesicles can go to one of two places. The first is the active zone. After being refilled, the vesicle can move to the active zone, dock, and release its transmitter when an action potential invades the axon terminal, just as happened a moment before. The second place they can go to is into the reserve pool of vesicles. To enter the reserve pool, the vesicle has to bind a protein that we haven't mentioned yet, synapsin. And this requires some explanation. The vesicles at and around the active zone where fusion and release occur are called the readily releasable pool of vesicles. If these were the only vesicles available for release, the synapse would run out of the vesicles very, very quickly. To maintain an adequate supply of vesicles, there is a large number of vesicles located just away from the active zone. These vesicles are called the reserved pool. But the vesicles in the reserved pool are not just floating freely in the exoplasm. Rather, they are tethered to actin filaments, which form part of the cell's cytoskeleton. Vesicles cannot normally bind to actin cytoskeleton, but they can if they first bind synapsin, the final protein that we consider. Synapsin bound to the vesicle connects the vesicle to the actin cytoskeleton. Here is how it works. The vesicles in the reserve pool are freed and can migrate to the active zone where they are phosphorylated, as phosphorylation of synapsin causes the synapsin to disassociate from the vesicle. The phosphorylation is triggered by the influx of calcium. The idea here is that there is a calcium binding protein called calmodulin that we will hear a great deal more about in later lectures on synaptic plasticity. In this case, when an action potential allows for the influx of calcium, calcium not only triggers fusion as discussed previously, but also binds to the calmodulin. The activated calmodulin then activates a protein kinase. It is the active protein kinase that then phosphorylates synapsin, as shown here. Once the vesicle is free of synapsin, it migrates to the active zone, where it can dock and release transmitter. Subsequently, the phosphatases dephosphorylate synapsin, thereby allowing it again to bind to vesicles, which allows them to replenish the reserve pool. Calcium then plays two roles in vesicular release. First, it triggers the fusion of the membranes of the vesicle and axon terminal, thereby resulting in transmitter release. Second, it activates calmodulin and then protein kinase, which phosphorylates the synapsins on the vesicles in the reserve pool, thereby allowing those vesicles to migrate to the active zone, dock, and release their transmitter. Together with vesicle recycling, these features maintain the synapse and keep it functional even when the axon is generating a high rate of action potentials and a high rate of synaptic activity. So let's briefly review the 7 proteins involved in fusion and recycling. The first 3 proteins are for docking and fusion. The first are the axonal snares. The second are the vesicular snares, both of which are required for docking. The third is synaptotagmin, the calcium binding protein required for the calcium-induced final fusion of the axonal and vesicular membranes. The next 3 proteins, that is the 4th, 5th, and 6th, are critical for vesicle recycling. The 4th are the adaptins that form a primer on the membrane upon which the 5th protein, clathrin, binds. Clathrin then accretes onto the adaptin primer to form a spherical cage around the budding reformed vesicle. The 6th protein is dynamin, and dynamin acts like a scissor to snip off the neck of the formed vesicle and thereby free the formed vesicle from the axonal membrane. The 7th protein is synapsin, and synapsin binds vesicles to the actin scaffolding in the reserved pool of vesicles.